A revolutionary battery. Scientists have developed a working laboratory demonstrator of a lithium oxygen battery which has very high energy density, is more than 90% efficient, and can be recharged more than 2000 times, showing how several of the problems impeding the practical development of the so called ultimate battery could be overcome. Lithium oxygen or lithium air batteries have been touted as the ultimate batteries due to their theoretical energy density, which is 10 times that of a lithium ion battery. Such a high energy density would be comparable to that of gasoline and would enable an electric car with a battery that is a fifth the cost and a fifth the weight of those currently on the market to drive from London to Edinburgh on a single charge. However, as is the case with other next generation batteries, there are several practical challenges that need to be addressed before lithium air batteries become a viable alternative to gasoline. Now, researchers from the University of Cambridge have demonstrated how some of these obstacles may be overcome and developed a lab based demonstrator of a lithium oxygen battery which has higher capacity, increased energy efficiency, and improved stability over previous attempts. Their demonstrator relies on a highly porous, fluffy carbon electrode made from graphene comprising of one atom thick sheets of carbon atoms and additives that alter the chemical reaction at work in the battery, making it more stable and more efficient. While the results reported in the journal Science are promising, the researchers cautions that a practical lithium-air battery still remains at least a decade away. What we have achieved is a significant advance for this technology and suggests whole new area for research. We haven't solved all the problems inherent to this chemistry, but our results do show routes forward towards a practical device, said Professor Claire Gray of Cambridge's Department of Chemistry, the paper's senior author. Many of the technologies we use every day have been getting smaller, faster, and cheaper every year, with the notable exception of batteries. Apart from the possibility of a smartphone, which lasts for days without needing to be charged, the challenges associated with making a better battery are holding back the widespread adoption of two major clean technologies, electric cars and grid scale storage for solar power. In their simplest form, batteries are made of three components: a positive electrode, a negative electrode, and an electrolyte, said Dr. Tu Liu, also from the Department of Chemistry and the paper's first author. In the lithium ion batteries used in laptops and smartphones, the negative electrode is made of graphite, a form of carbon, and the positive electrode is made of a metal oxide, such as lithium cobalt oxide, and the electrolyte is a lithium salt dissolved in an organic solvent. The action of the battery depends on the movement of lithium ions between the electrodes. These batteries are light, but their capacity deteriorates with age and their relatively low energy densities mean that they need to be recharged frequently. In lithium air batteries, however, the charge of the electrodes is reversed. Over the past decade, researchers have been developing various alternatives to lithium ion batteries, and lithium air batteries are considered the ultimate in next generation energy storage because of their extremely high energy density. However, previous attempts are working demonstrator have had low efficiency, poor rate performance, unwanted chemical reactions, and can only be cycled in pure oxygen. What Liu, Gray, and their colleagues have developed uses a very different chemistry than earlier attempts at a non aqueous lithium air battery, relying on lithium hydroxide instead of lithium peroxide. With the addition of water and the use of lithium iodide as a mediator, their battery showed far less of the chemical reactions which can cause cells to die, making it far more stable after multiple charge and discharge cycles. By precisely engineering the structure of the positive and negative electrodes, changing it to a highly porous form of graphene, adding lithium iodide, and changing the chemical makeup of the electrolyte, the researchers were able to reduce the voltage gap between charge and discharge to zero point 0.2 volts. A small voltage gap equals a more efficient battery. Previous versions of a lithium air battery have only managed to get the gap down to zero point 0.5 to 1.0 volts, whereas zero point 0.2 volts is closer to that lithium ion, equating to an energy efficiency of 93%. The highly porous graphene electrode also greatly increases the capacity of the demonstrator, though only at certain rates of charge and discharge. Other issues include finding a way to protect the metal electrode so that it doesn't form spindly lithium metal fibers known as dendrites, which can cause batteries to explode if they grow too much and short circuit the battery. Additionally, the demonstrator can be recycled only in pure oxygen, while the air around us also contains carbon dioxide, nitrogen, and moisture, all of which are generally harmful to the metal electrode. There's still a lot of work to do, said Mark Fisher. But what we have seen here suggest that there are ways to solve these problems. Maybe we have just got to look at things a little differently. While there are still plenty of fundamental studies that remain to be done to iron out some of the mechanistic details, the current results are external exciting. We are still very much at the development stage, but we have shown that there are solutions to some of the tough problems associated with this technology, said Johnson Matthey, another researcher.